Good afternoon. I am B. Bhuvaneshwari, Department of Physics, K. Ramakrishnan College of Technology, Trichy. I would like to welcome the resource person Dr. P. Mani Prakaspati, Assistant Professor in Physics, Anna University, BIT Campus, Trichy, on behalf of our management and faculties. Today, our resource person is going to present a webinar on thin films and overview. He did his research on thin film physics and he published about 15 papers in international journal. And he also received 3 best paper awards, out of which 2 in international conference and 1 in national conference. He delivered about 75 talks in schools and colleges and also 15 talks and quiz in All India Radio. So once again, I would like to welcome this eminent person for presenting this webinar. And I also welcome the participants such as faculties of various colleges, research scholars and students. I welcome you all to the webinar. Thank you.
Very good morning, friends. Thin films overview. First of all, I want to thank K. Ramakrishna College of Technology, Samebram, Tiruchi, Chairman Ramakrishnan sir, Director Kupusamy sir, HOD Sarvanakumar sir, Principal Muruganandam sir, and the coordinators of this event, Professor Tandabani, Professor Kailvili Nangai, Professor Bhuvaneshwari, Professor Nalini. And I want to mention my supporting team, Engineer Bhaskaran, Professor Kumar, and my students, Protractor Immediate Past President J. Jerry Shobat, Protractor President R. Mohammedan, and finally the participants. You very good afternoon, all of you. I feel great to with you to welcome all of you traditionally. And I thank the institutions educated me. I thank the institutions appointed me. And I want to share one of my prestigious moments in my life. I worked under the leadership of our Excellency Dr. APJ Abdul Kalam in Pura scheme, providing urban amenities in rural areas. And I'm with great scientist, Dr. A. Sivadanu Pillai, and I'm in the corporate office of BrahMos, which is used to raise the colors of each and every Indian, the great missile, cruise missile. Yeah, we will enter into the subject, thin film and overview. First of all, we may see the contents of this lecture. Actually, we may start with introductions to thin film, that is basics of thin films. Applications of thin film. Before starting any subject, if we are discussing the applications, it may be quite interesting. So we may start with applications, and then what is solar cell, what is photovoltaic effect, then what are the criteria for material selection and substrates, then deciding factors of a film, material's thickness and surface roughness, various available deposition methods, and my own deposition method, successive ionic layer absorption and reaction method, and then material preparation, various materials, their characterization, results we may discuss, and finally some of the papers. Then what is thin film? Thin film is a layer of material ranging from fractions of nanometer to several micrometers in thickness. It's less than 1 micron, 10,000 Armstrong to 1,000 nanometers. And film is layer of material on a substrate, we know. And we are seeing the scale of thick and thin film. Here we are seeing the range again. Attractions of thin film. Why the world of scientists and industry are attracted towards thin film. It's aesthetic, lighter weight, non-breakable, simple fabrication, reliable and flexible, better performance, requires less fabrication temperature, manufacture, manufacturing required little material, low cost of production and size reduction. Then we see the different application. First of all, it's applied in bioactive coatings, hemocompatible coatings, and antibacterial, anti-fouling, self-cleaning coatings, and it improves the ability of batteries, solar cells, fuel cells, and for aesthetic coatings, then anti-wear coatings, anti-corrosion coatings, fire retardant coatings, magnetic thin films are used as electronic gadgets, and also for high power applications, and so many applications are there. We are taking these things. Then we can classify the applications as major applications as three. First one is sensors, then energy storage applications, for biological applications. We are seeing different sensors: biosensors, gas sensors, optical sensors, chemical sensors, and then energy, solar cells, supercapacitors, electrochemical cells, dye-sensitized solar cells, rechargeable batteries, organic cells, so many things are there. And biological applications, coatings like antimicrobial, anti-fouling, self-cleaning, tissue engineering, and we can classify like this also: biological applications, inorganic, organic, and they are applied in biosensing, implantable devices, tissue engineering, and drug delivery. And we can see the types of thin film sensors. So many types of sensors are there. And we may see the 5 different sensors: high temperature strain sensor, thin film thermocouple sensors, heat flux sensors, flow sensors, multifunctional sensors. And we can see the advantages of sensors over traditional sensors. This thin film sensors are lasting ability, and they are stable and precise, dependable and cheap, rapid response time, and the exact size allows for intimate placement, decreased need for external circuitry itself acts as a sensor. So small and compact, housing is easy, can deposit on ceramic materials and high-grade steels. Now we may enter into thin film solar cells. We are seeing how solar cells are working and how it's utilized for the home usage, and the excess is taken into grid. In the point number 1, solar panels convert sunlight to DC current, and 2, inverter converts DC electricity to AC. 3, take electricity for our home requirements, and 4, extra electricity is credited on grid. Solar cell and photocurrent. Here we are seeing the structure of solar cells, and it's having different layers. The top and bottom layers are the ohmic contacts layers, that is electrode. In this example, they are showing zinc oxide and molybdenum as electrodes. The topmost layer is here a glass material, and the thickness is mentioned as high, very low thickness, 5 millimeter, that is 5000 microns, right? 1 micron, the thickness of the thin film is 1 micron, and we know 5 millimeter is 5000 microns. Here we are seeing different layers: semiconductor negative layer, that in this example that is made by cadmium sulfide; semiconductor positive layer, that is made by copper indium gallium selenide. And how solar cell works: Sunlight contains packets of energy called photons. When the sunlight strikes the negative layer, the photons collide with some of the electrons in this material, causing them to move. We know that the movement of electrons is current. The electrons move to the positive layer. Any movement of electrical charge produces an electric current. And some of the successful solar cell materials: cadmium telluride, copper indium gallium diselenide, and amorphous thin film silicon. And we know one thing: the glass transmits short wavelength and opaque for longer wavelength. And we are seeing different layers of solar cells. Top layer is glass, highly transparent layer, window layer, and finally the absorber layer. And we may see about window material. It's highly essential for a solar cell, right? Normally, when photon incidents on a material, some of them may get reflected, some of them may get scattered, few of them may get transmitted to the next layer and got absorbed. So the first layer, window layer, should be free from reflection and scattering. It should transmit all the radiations falling on it. The efficiency increases with transparency of the window material. The material utilized for this purpose should be a highly transparent window materials. So we are seeing if 100% photons are falling on a material, 30% scatter may be there and 30% of reflection may be there. Only 40% of the photons are transmitted to the absorber layer. And material selection criteria: thin film material should be earth abundant, cost effective, sustainable, clean energy, and it should be eco-friendly also. Then photovoltaic effect: when light radiation is falling on the solar cell, voltage is developed across p-n junction in a semiconductor. It is known as photovoltaic effect. An electrical device which converts the light energy into electricity by the photovoltaic effect is called photovoltaic cell or solar cell. Okay, here we are seeing the photovoltaics effect in detail. Sunlight is composed of photons, we know, or particles of solar energy that contain various amounts of energy corresponding to the different wavelengths of solar spectrum. The electrons present in the valency band absorb energy and, being excited, jump to the conduction band and become free. These highly excited electrons are accelerated into different material by a built-in potential. This generates an electromotive force, and thus some of the light energy is converted into electric energy. And here we are seeing the history, efficiency based history of solar cell. Alexander Edmund Becquerel discovered photovoltaic effect in the year 1839. Charles Fritz achieved 1% efficiency in the year 1883. And Dept and Stora discovered the photovoltaic effect in cadmium sulfide CDS in the year 1932. And 6% of efficiency achieved in the year 1954 using cadmium sulfide. In the year 1985, University of South Wales achieved 20% of efficiency. 44.7% of efficiency achieved in the year 2013. And it's moving on. So many researchers are going to achieve the maximum efficiency. Deciding factors of coating behavior: first, doping, pH values, counterions, concentrations, coating duration, coating methods, individual rinsing, complexing agents, coating thickness, annealing temperature, and pre-treatment of the substrates also playing vital role. And film thickness. We can find the film thickness in two ways. Thickness can be measured during deposition and can be measured after finishing the coating. Physical properties of a thin film are highly dependent on their thickness only. So it's playing vital role in the thin films. And we are seeing the experimental setup to find the thickness, and by using this apparatus we are finding the film thickness, and so many methods also there to find the thickness. And roughness is one of the very important criteria for thin films. Roughness can influence all film properties such as mechanical, electrical, magnetic, and optical. So roughness types, the mechanisms of their origin, roughness measurement, and roughness quantifications needs to be taken into the consideration. And now we may see the preparation of glass substrate. Here we are taking clinical glass slides for our present work. Here we may take different transparent substrates also. For this treatment we used in our lab the clinical glass plates, and the clinical glass plates may be 75 mm length, 25 mm width, 1 millimeter thickness, and they are cleaned and pre-treated by immersing them in concentrated nitric acid for 2 to 3 days, washed in detergent solution, then degreased with acetone, rinsed in distilled water, and dried in air. So these are the 5 important steps to clean the glass substrate, and so many steps also there, sonication and some other steps. And then thin film deposition are broadly classified into physical process and chemical process. In physical process, evaporation and sputtering techniques are playing vital role. In evaporation, electron beam evaporation, arc and flash evaporation, ion plating, laser ablation, molecular beam epitaxy, electro beam evaporation are playing vital role. And then in sputtering, RF sputtering, DC sputtering, magnetron sputtering are playing vital role. Ion beam sputtering also there. In chemical process, plating is electroplating and electroless plating, solid gel method, dipping, spraying, spin coating, CVD, under CVD, MOCVD, PECVD, ALD, so many methods are there. And this is one of the classifications. And first we may see electron beam evaporation. Here, a stream of electrons by a voltage is focused onto the surface of the material, which is contained in water-cooled crucible. The kinetic energy of the electron is transferred rapidly into thermal energy, and the material melts at the surface and evaporates. Then vapors are deposited on substrates. ARC evaporation. Here the material is evaporated by the action of vacuum arcs and deposited on a substrate. Arc is occurring in regions of a few micrometers in size and carrying very high current densities. Sputtering technique. Here the particles are ejected by bombarding with positive ions. Released matter is condensed on the targeted area to form thin film. This method produces the films with high uniform thickness with good adhesion. We know different types of sputtering: conventional DC sputtering, AC sputtering, triode sputtering, RF sputtering, magnetron reactive sputtering, RF ion beam sputtering, and etc. Here we are seeing different types of sputtering, single element and compound, 2 and 3. Here the sputtering gas is allowed through this area. Whenever the materials evaporated, they are traveling towards the target, sputtering target. The argon gas is helping to move or take the material towards the sputtering target. We are seeing this here. Then chemical methods, chemical bath, deposition. We are seeing the experimental setup of the chemical bath deposition. We are having heater with beaker setup. Here we are placing the clinical glass plate here, and we are having a stand, rotor, thermometer, precursor solution, oil filled bath, magnetic needle, everything. Here, chemicals are taken in bath and dissolved using the appropriate solvents. It may heat it up, it requires, and stirred to get a homogeneous mixture. For the standardized period of time, the substrate may be immersed in the bath and washed to remove loosely bonded particles. Finally, they may be washed with deionized water and dried in air. It's simple method, and we are seeing chemical bath reactor, electrochemical deposition. We know here anode and a cathode are immersed in a suitable electrolyte. On passing electric current, material is deposited on the cathode. Here we are seeing the setup. Electroplated rod is here, gold rod, metal rod, and applied voltage gold cations are deposited. Okay. Spray pyrolysis. There are two types of spray pyrolysis. One is conventional and the modern setup. Another one with preheat treatment. In the conventional method, a diluted solution is sprayed from an atomizer onto a heated substrate in normal and controlled atmosphere using high pressure argon, nitrogen, or air as spraying gas. Homogeneous films are obtained by rotating the substrate or rotating the sprayer. Here we are seeing spray gun, reservoir for precursor solution and controlling valves, compressor with pressure regulator, spray nozzle, substrate, thermocouple, and steel plate, heater, everything we are seeing. Then electroless deposition. Here, no electrode potential is applied, as in the case of electrode deposition. Chemical reduction is done using metal. The metal acts as a catalyst. Sol gel spin coating technique. Here, using the action of centrifugal force, the spin coating of thin films achieved. The drops from the sol gel spread out uniformly to form thin film on the substrate while the substrate is spinning. Here, the sol gel is placed at the center of the substrate. The quality of the film may be varied by changing the parameters like concentration of precursor solute, gelation stage of the sol gel, heat treatment temperature, atmosphere, the turntable, spin rate, and time. Here we are seeing sol gel method. Chemical vapor deposition, the famous CVD technique. Here the materials with high vapor pressure, thermal instability, and high volatility are taken for CVD method for preparation. These materials are carried by an inert gas like argon or nitrogen from a heated bubbler through a heated line to a reaction chamber where oxygen or water vapor is introduced. The vapor decomposes and the homogeneous film is deposited on heated substrate. The appropriate volatile dopant is introduced from another heater bubbler into the reaction chamber for doping. There are different types of CVD, such as photochemical vapor deposition, plasma enhanced CVD, metal organic CVD, and laser CVD, etc. Now we are seeing pulsed laser deposition, shortly called PLD. With the help of laser, the target is evaporated towards the sample, and we are using different elements to coat on the sample with the help of laser, it's evaporated and coated on the sample as a layer, thin layer in substrate. Okay, then we may go to dip coating. Here we are having step-by-step process of coating. In dip coating, we are immersing clinical glass plate in a beaker, which is having the solution for a predetermined period of time. After a particular time, we are withdrawing the glass plate. There is a formation of wet layer, and then solvent is evaporating. Then for a particular period of cycles, we can doing the same process again and again, and we are having and we are getting very good coating of thin films. Then frequently used deposition methods: PVD, CVD, ECD, MOCVD, CVD, sputtering techniques, plasma techniques, and spray pyrolysis, dip coating, spin coating, and finally now SILAR we are using in our lab. SILAR is successive ionic layer absorption and reaction. Thin films are obtained by immersing the substrate into separately placed cationic and anionic precursors and rinsing between every immersion with ion exchanged water. This method is also known as a modified version of chemical deposition. Here we are seeing 4 different beakers, and first one is immersion in cationic precursor, and the third one is anionic precursor, and these two B and D are deionized water, right? This is the setup, and there are 3 different setups: for binary, for ternary, for quaternary compounds. This setup is for quaternary compounds. In the previous binary method, here we are having 2 different precursors, A and C. One is anionic, another one is cationic solution. And here we may have 8 different beakers, right? And the specifications of SILAR controller. Here we have so many setups to produce the thin film in a very quality manner. Here we are taking 100 ml beaker, and the concentration is fixed according to our need, and we may fix the temperature as 31 degrees C if the process is taken place in room temperature. And then if you are interested, we may add complexing agents. In our process, we used TEA and EDTA. In the first one, tin nitrate, along with tin nitrate and along with copper nitrate. It's okay. Then we may fix start position as 0. Then dip length for 75 millimeters. Dip speed. Dip speed in the sense immersing the glass plate inside the beaker slowly. That is 5 millimeter per second. And retrieval speed, retrieving the glass plate from the beaker, that is 4 millimeter per second. Dip duration, that is immersion time, 35 seconds. The glass plate is immersed in the beaker. X dip duration, that is outside the beaker, just above the liquid, is X dip duration, that is for 4 seconds. The same cycle is repeated for 25 times, and it's soluble in water, right? These are the deposition parameters in SILAR controller. Here we are having 4 different steps of SILAR deposition process. The first one is absorption. In the first step, cations present in the precursor solution are absorbed on the surface of substrate and form Helmholtz electric double layer. This layer is composed of two layers. The inner, that is positively charged, and the outer is negatively charged. The positive layer consists of the cations and the negative layer counter ions of the cations. Second process is rinsing. First rinsing, the excess adsorbed ions are rinsed away from the diffusion layer by the second step. This results in saturated electrical double layer. And the reaction, in the reaction step, the anions from anionic precursor solution are introduced to the system. Due to the low stability of the material, a solid substance is formed on the interface. This process involves the reaction of surface specifies with the anionic precursor and second rinsing after the reaction. The excess and unreacted spaces of used material are removed in this step. By repeating these cycles, a thin layer of material can be deposited. Deposition process. In Silla deposition, we are taking copper sulfate thin films as an example. First, pre-cleaned glass substrates are immersed in cationic precursor for 30 seconds for the adsorption of Cu ions. Then, it was immersed in distilled water for 30 seconds in order to remove the deadsorbed ions. Then, substrates were again immersed in anionic precursor for 30 seconds for adsorption and reaction of sulfur ions. Unreacted sulfur ions were removed by rinsing them in distilled water for 30 seconds. It's for binary, the same step is followed for ternary and quaternary. Here, the fine tuning of cellular controller for our required times of interval and everything. Here we are using copper nitrate and sodium sulfate, and we are using deionized water in between them. Finally, we are getting copper sulfate. Okay, advantages. So many advantages are there. Excellent material utilization efficiency and layer by layer coating. Wastage of material is reduced here, and the thickness of the material film can be controlled easily. Then thick and thin film can be prepared by this method in inexpensive, simple, convenient for large area deposition on any type of substrate. And we can deposit compound materials such as insulators, semiconductors, metals, glass, etc. on variety of substrates such as insulators, semiconductors, metals, glass, etc. And we can coat the films with required and appropriate quality by changing the parameters. And this method doesn't need a controlled environment, but it has temperature controlled system. It doesn't require vacuum at any stage. It's a simple one. Can obtain the coating of equal number of anion and cations at low temperature process. It also avoids oxidation and corrosion of the substance. Extremely easy to dope film and doesn't require a high quality target or substrates. There is no restrictions on substrate materials, dimensions, and its surface profiles. It can be carried out in glass beakers simply. Better orientation and improved grain structure can be obtained from this method. Thus, any insoluble surface to which the solution has free access will be suitable substrate for the deposition. And we may see different characterization, results, and techniques. First, we are seeing influence of molar concentration on pure copper sulfide thin film by Siller method. We are seeing the characteristics of copper sulfide and applications of copper sulfide thin films. Material preparation for pure copper sulfide. And here we are seeing XRD pattern. For first film, it is in amorphous nature. The second one is in polycrystalline nature. We are seeing the calculations. And here, the first one is in polycrystalline, and the next one is amorphous. And we are seeing the same result. Here, the film is coated uniformly and homogeneously. And we are seeing topography analysis. Here we are getting the results as grain size, surface roughness, surface height for 5 and 10 micrometers. And wavelength versus absorption. Transmittance curve. Band gap measurement. For this copper sulfate of 1:1 ratio, we are getting 1.92 and 2.32. In between these two, the band gaps are coming. The lowest one is 1.92, the maximum is 2.32. And we are seeing the influence of molar concentration on optical properties of copper sulfate thin films, 1:1 and 1:2 ratio. For 1:2 ratio, the minimum band gap value is 1.86. The maximum is 2.21 electron volts. Here, as a conclusion of the pure copper sulfide thin films, efficiency may be increased by trial and error method using various concentration, film layers, immersion time, and reaction time, etc. Then, TEA added copper sulfide thin films in cellular method, the usual setup, and pre-cleaned glass substrates are immersed in cationic precursor for 30 seconds for the adsorption of copper ions. Then it was immersed in distilled water for 30 seconds in order to remove the deabsorbed ions. Substrate were again immersed in ionic precursor for 30 seconds for adsorption and reaction of sulfur ions. Unreacted sulfur ions were removed by rinsing them in distilled water for 30 seconds. As prepared material is characterized. Here we are having single peaks. It's showing the amorphous nature. We are seeing some result uniform coating. And AFM analysis, we are getting grain size, surface roughness, surface height. We can see the uniform smooth coating here. Optical analysis absorption. Absorption is ranging from 0.07 to 0.20 for our different molar concentration. This is transmittance curve. Molar concentration ranges from 0.05 to 0.25 m. Transmittance is between 83% to 95%, and band gap is ranging from 1.92 to 2.25 electron volts. And EDTA added copper sulfide. This is experimental setup. In STEM, we are seeing the uniform coating, also in AFM. Optical analysis, UV absorbance is showing 0.067 to 0.199 on strong unit absorptions for various molar concentrations, and transmittance ranges between 81% to 95%. Band gap is ranging between 1.8 to 2.20 for this EDTA added copper sulfate solution. Influence of molar concentration on optical properties are ranging here. Then TEA added tin sulfide. Tin sulfide belongs to 4th to 6th group with p-type electrical conductivity. It shares good qualities with FeS2 like cost, earth abundance, least toxicity, and stability. It has unique position among the metal sulfides. It attracts considerable interest in the field of photovoltaic energy conversion. So, as in the earlier method, we are coating tin sulfide. These are the deposition parameters. We are preparing like this. XRD patterns are coming like this. Is showing the materials. We are doing the calculations. FTIR is showing different vibrations, wave number range. It confirms the presence of absorbed water, sulfide group, tin sulfide, organic contamination, etc. Then is showing the uniform coating and structures. Then optical absorbance of tin sulfide thin films with the TEA. It ranges between 0.1 to 0.08. Optical transmittance ranges from 92.23 to 93.99. Then band gap analysis. It ranges between 1.89 to 2.44 electron volts. And now we are moving to EDTA added tin sulfide. As in earlier cases, we are preparing tin sulfide with the EDTA. Here also we are doing these experiments in room temperature and we are not annealing, so we are getting amorphous. We are seeing the uniform doping of material using SIM and AFM. FTIR analysis confirms the presence of water, sulfide group, organic contaminations, and we are seeing absorption spectra, wavelength versus transmission. It is ranging between 86 to 94%. Band gap for EDTA added tin sulfide 2.02 to 2.42 electron volts. Now we are moving to CTS added TEA, copper tin sulfide with TEA, triethanolamine. Here we are, it's a ternary. Copper tin sulfide belongs to this group. It shares good qualities with FeS2 like cost, earth abundance, least toxicity, and stability. CTS has a unique position among the metal sulfides. It attracts considerable interest in the field of photovoltaic energy conversion. Now we are seeing the experimental setup. For 3 elements, we are having 3 different beakers. In between the beakers, we are having deionized water to rinse, and this was deposited copper nitrate plus TEA in first beaker, then water, sodium sulfide in next beaker, water next, then tin nitrate and TEA, then water. Finally, we are getting copper tin sulfide. So these are the deposition parameters. Material preparation we know, and we are getting amorphous. Surface morphology is good for this. We are seeing semi-majors in various sizes for copper tin sulfide in various molar concentration. Surface topography by AFM. We are seeing different grain sizes, surface roughness, surface height for different molar concentrations. We can see uniform coating. Then FTIR spectrum for this CTS added with TEA. we can confirm tin sulfide presence of water and contamination, everything. And then now we are seeing optical absorbance, transmittance, they are perfect. And band gap analysis, the band gap is ranging from 1.79 to for the maximum of 2.28, right? It's the value is going like this for various molar concentration. Okay, here we are comparing the material we have taken for pure copper sulfide in the ratios 1 is to 1 and 1 is to 2. Likewise, the band gap is ranging from 2.05 to 2.26, 1.86 to 2.21. And for TE added copper sulfide and tin sulfide, it's ranging between 1.9 to 2.25. For tin sulfide with the TEA, 1.89 to 2.44. With the EDTA, both copper sulfide and tin sulfide. Copper sulfide with the EDTA, 1.82 to 2.20. EDTA with tin sulfide is 2.02, right? And here we are seeing the minimum of 1.79 and the maximum of 2.28 electron volts. Conclusion for the experiment on the whole, among all the materials taken for investigation, T added copper doped tin sulfide, that is TCS, is having low band gap energy as 1.79 electron volt. Maximum band gap energy for this is 2.28 electron volt. This is observed for T added CTS. In binary, CUS with EDTA is having low band gap, that is 1.82 electron volts, and tin sulfide with the TA is having 1.89 electron volt. TA and EDTA may be suitable to release free electrons for the respective materials. Now, we may see thin film in the nanotechnology. Nanocomposite materials shows improved mechanical properties due to so-called size effect. The final functional effects which can be obtained are oxidation resistance, high adherence, low thermal conductivity, wear resistance, high toughness, and hardness. Primarily, the magnetron sputtering method is used for deposition due to the high purity and low level of defects which are allowed by this process. And we are having different coatings, optical coatings, decorative coatings, biomedical coatings, self-cleaning coatings, anti-reflective coating, scratch resistance coatings, UV and IR reflective coatings, AG and AI coated, AL coated mirrors by a vaporization process, etc. And industrial applications of thin film semiconductors, transistors, compact disc, smart windows, conductive stack, photographic lenses, solar cell, multifunctional coatings, telecommunication devices, anti-corrosion and wearing coatings, memories, magneto-optic memories, ICs, computer chips, MEMS, and magneto-optic drives and electro-optic coatings. Future may be like this for solar cells. And we are seeing the growth of devices, thin film PZT devices, the companies who is doing this, and global thin film solar market in 2016 to 2023 forecasted one. The materials used are cadmium telluride, CDTE, cadmium indium gallium selenide, CAGS, amorphous thin film silicon also in the race. And we are seeing solar PV thin film processing, cost analysis, and in Indian view, solar demand forecast is like this. Okay, thank you for your attention. Some of the papers published by our team in JMSC, tin sulfide EDTA, in applied surface science, TEA with iron sulfide, CDS film, Indian Journal of Pure and Applied Sciences, Applied Physics, American Journal of Engineering and Applied Science, cadmium sulfate nanofilms. Okay, thank you for your patience. Now we may go for question and answer sessions. Thanks a lot for your patience again. Thank you very much.
Thank you, sir, for your valuable section. Dear students, you are asked to, if you have any doubts, please raise your doubts in chat box. Okay, sir, we have some few questions. First question was, what is the role of window layer, sir?
Role of window layer. Okay. Window layer is the first layer of solar cell, and it should be free from reflection and scattering. It should transmit all the radiations falling on it. The efficiency increases with transparency of the window materials. So the window is highly essential. Window layer is highly essential for a thin film. This layer only absorbs all the radiations. So it must be free from reflection and scattering.
Okay,
Next
sir.
question.
Sir, one of student raised a question. Where the organic photovoltaic devices applied?
Okay, organic photovoltaic devices. Okay.
Yes, sir.
Okay. Organic photovoltaic devices rely on a mixture of light-sensitive polymers or small molecules and fullerene-like compounds to absorb light and set the electricity generating events in motion. The compounds are typically blended in a nanoscale network known as bulk heterojunction. That arrangement mediates efficiency charge separation by providing a large area of contact between the organic molecules and electron donor and the fullerenes. The fullerenes is electron acceptor and the organic molecule is an electron donor. As emerging photovoltaic technologies, organic photovoltaic modules are thin, lightweight, and flexible. They will suited to being placed on the outsides of buildings and on irregularly shaped products such as fabrics for backpacks on tents also we may have. It's a recent technique. Next
Okay,
question.
sir. Okay, sir. How is sunlight turned into electricity?
It's basic one. In solar cells, photons in the light energy knocks the electrons in the material. Getting this energy, electrons start moving. We know that flow of electron is electric current. So the conversion of, not conversion, photon induces the movement of electrons. In this way, sunlight turned into electricity. Next question.
Okay, sir. Okay, sir. How dye-sandalized solar cells work?
Dye-sensitized
Okay, sir.
solar cell.
Okay, sir.
Dye-sensitized solar cells
Works.
Working of dye-sensitized solar cell,
Yes,
DSSC. Okay. In DSSC, light transmitted by the transparent electrode of DSSC is absorbed by a dye, which coats, for example, TiO2 nanoparticles. The process forms electron hole pairs. The electron travel through titanium oxide layer towards one electrode, and holes travel through an electrolyte towards the other electrode. It generates the electric current. An appreciable quantity of electricity can be generated from sunlight by means of an inexpensive and easily produced device. Their work touched off a wave of DSSC research and led to the founding of several startup companies. All photovoltaic devices generate electricity through a series of light absorption, electronic excitation, and charge separation events. Unlike in conventional solar cells, where these events occur in a single layer of silicon, in DSSCs, the events occur in separate molecular layers. This is the working of DSSC.
Okay, sir. Another one
Next.
question, sir. How and why N-type and P-type compounds formed in solar cell?
Okay. I think so many students are here. First year engineering students, they are asking basic questions in their syllabus. Okay, good. Okay, N-type, P-type compounds formed in solar cell. How and why? Okay. Sunlight is absorbed into the photovoltaic material. It knocks free electrons in the material. This allows the electrons to flow freely and creates an electric current. With few free electrons, there is very little flow of current. So, second or third and fifth or sixth group impurities are added to the fourth group element to increase its current carrying properties. This process is called doping, we know. For example, silicon is doped to create negatively charged silicon, or referred as N-type. And if you are doping with P-type, silicon is doped to create positively charged silicon, it's referred as P-type. When energy is added to N-type silicon, there are lot and lots of free electrons formed, and they are present within the structure. This N-type silicon is placed next to the P-type silicon. It causes the free electrons in N-type silicon to rush towards the holes in the P-type silicon, which creates the current flow. That's all.
Okay, sir. Sir, another one question. How many atoms thick is a thin film?
How many atoms thick is a thin film?
Thin film, yes.
Okay, we'll take. Suppose if the thickness of a thin film is considered as 1 nanometer, the diameter of an atom considered as 0.2 nanometers. So, diameter of atom is 0.2 nanometers, film thickness 1 nanometer. So, there will be 5 different layers of atoms in a monolayer of a thin film. Right. I think it's okay. Next.
So, what is the difference between thin and thick film?
Difference between thin and thick film.
Thick film,
oh, good. Thick film is around 1,000 times thicker than thin film. Thickness of a thin film lies between 100 micrometers to 10,000 Armstrong. But thickness of thin film is less than 1 micron. That is, thickness of thin film lies between 10,000 Armstrong to 1,000 nanometers. For thick film, 100 micrometers to 10,000 Armstrong. For thin film, 10,000 Armstrong to 1,000 nanometers. Its thick film is around 1,000 times thicker than thin film. Okay. Next question.
Okay, sir. What is the need for uniform coating of thin films?
Okay, uniform coating of thin films.
Thin films, sir. Yes.
Uniformity is necessary to meet the performance specs in any application, regardless of deposition method. You might require a very fine film coating if it is a little too thick in certain areas. It can have a negative effect on performance. So the surface must be uniform. So the coating must be uniform one. So uniformity in thin film is highly essential one. Next.
Okay, sir. One of our participants asked to suggest some good materials for quantum dot solar cells.
Okay, good materials for BS. Okay. Okay, quantum dot solar cells, nanocrystals of semiconducting metal chalcogenides like CDS, CDSC, PBS, and PBSC, and other materials are used. Actually, they function as light absorbing material in the device This method is low-cost solution phase chemistry method and used to high-speed printing techniques. Okay, so the answer is materials like CDS, CDSC, PBS, and PBSC. Next.
Okay, sir. Sir, one of our students also asked, what are the recent solar cells?
Recent solar cells. Yeah, already we discussed dye-sensitized solar cells, organic solar cells, and perovskite solar cells. These three are the recent solar cells.
Okay, sir.
Next.
Is electrically operating coatings available?
Yeah, it's available, electrically operated coatings. Okay, thin layers of elemental metals like copper, aluminum, gold, or silver, etc., and alloys and their alloys have found numerous applications in electrical devices. Due to their high electrical conductivity, they are able to transport electrical currents or supply voltage. So, in this way, we can understand the electrically operating coatings. Okay,
Yes,
next.
sir. Thank you, sir.
Okay, thank you,
Sir.
thank you.
Yes.
If you have any doubts, furthermore, kindly send your doubts, send your questions to the mail ID given in the chat box. Thank you, K. Ramakrishnan College of Technology, the principal, director, chairman, and HOD, physics HOD Tandabani, and other teaching members and technical committee, immediate past president of Rotary Club of Anna University, Protractor Jerry Shobert, and president Protractor Navamadan for your technical support. Thank you very much. Thank you, participants, for your patience. Thanks a lot. Thank you very much. Okay,
Thank you,
bye.
sir.